Welcome to NSTA Web Seminars, where you can find live interactive learning at your desktop. Tonight's presentation is in partnership with the American Chemical Society, and it is titled The Periodic Table and Bonding, Introducing a Free Online Resource for Middle School Chemistry. Tonight's presenter is James Kessler. My name is Bryn Slate, and I will be moderating the program tonight, and we have Jeff Lehman online with us to provide technical support. I wanted to remind everyone to visit the NSTA Learning Center, which is your online portal for professional learning for science educators, and we have over 10,200 resources for you to check out. You'll find in the Learning Center that over 3,500 of those are free and that you can add them to your library to access when it's convenient for you. Our community forums are a great place to interact with other science teachers and discuss the issues that are pertinent to your classroom. We have online advisors who are willing and able to assist you and help you find the resources that you need there in the Learning Center. We also have free tools that you can use to organize your professional learning and reach your goals and document that progress. It's all available by going to learningcenter.nsta.org. At this point, I'd like to go ahead and introduce Jim. He is the manager of the K-8 Science Education Office there at the American Chemical Society. I wanted to also make a note that we do have Adam Boyd from ACS online with us as well to provide support there in the chat window and answer your questions. So now I'll go ahead and turn it over to Jim. Welcome, Jim.
Thanks, Bryn. Hi, everybody. Thanks a lot for coming. Tonight's session, as you know by now, is about middleschoolchemistry.com, and we're going to be doing Chapter 4, the periodic table and bonding. Basically, middleschoolchemistry.com is a free online resource for teaching basic concepts in chemistry at the middle school level. We did 6 chapters. They all contain completely developed lesson plans. There's 5 or so lesson plans in the first in chapters, maybe 1, 2, and 3, and then we had more lessons in chapters 4, 5, and 6. Basically, the idea behind the resource is to help students understand everyday observations on the molecular level. Most of what we do, kids only need very simple equipment to do it. And the idea is that they can understand the world around them on that small level. And also to help kids understand how to design and conduct scientific experiments. So it's really about the content and the process. It's sort of a nice combination of both. We wanted to take you guys to the website to take a quick look around. I think Bryn can do that. Bryn, can you take us to middleschoolchemistry.com real quick, and we'll look around a little bit?
Sure thing, Jim. And I wanted to let everyone know what we're going to do tonight is we are going to push out this website for you to explore. And Jim is going to navigate us through the website and let you know where to go for now. But the window will be open on your computer in your browser so that you can leave that open and explore it later after the program and continue to poke around. So what's going to happen is as soon as I click OK here, you're going to see that middleschoolchemistry.com website come to the front of your screen, and then Jim's simply going to tell you what to click on. And back to you, Jim, to navigate us through the site.
Okay. So by now, I hope most people see this main page here. You can scroll down a little bit until you see View the Lessons. I like to get into the content of middleschoolchemistry.com by clicking View the Lessons. You can go in different ways. You could click on Lesson Plans up at the upper left, but I like View the Lessons. So could we click on this big button here that's to the left of the guy looking at the molecules, View the Lessons? And what you should see is a series of chapters. The whole topic, the category is called Lesson Plans, but it's based on chapters. Chapter 1 is about matter, and then Chapter 2, changes of state, Chapter 3, density. If you continue to scroll down, you'll get to what we're going to do today, Chapter 4, the periodic table and bonding, and then you can see that there's Chapters 5 and 6. And all of those numbered lessons there are lesson plans that we put together. They contain multimedia, video, and molecular animations, and there's lots of stuff in there. So you guys, why don't we just, for instance, well, before we pick any lesson, I want to show you one thing that it's not totally obvious, but for instance, where it says Chapter 4, the periodic table and bonding, if you click on that, it'll take you to a place where if you scroll down, you can see that we have a student reading about Chapter 4. There's a lot of teacher background that you can look at to refresh your recollection about different aspects of the periodic table and bonding. There are test bank questions. If you want to create a test, we have, true, false, multiple choice, short answer, essay type questions. So I wanted to show you that because it's not so obvious that where the stuff is. Now we can go. We could go into a lesson here, protons, neutrons, and electrons. If everybody clicks on that, I hope you guys are following this more or less. Here is an actual lesson plan. We always start with the same sort of thing, the key concepts, a summary. If you scroll down, you'll see the objective. There's an evaluation, which is really the student activity sheet. And I wanted to point out that the lessons are all in the 5E kind of format. They include engage, explore, explain, evaluate, and extend. That's a pretty classic formulation of a lesson plan. And if you guys are still with me here, on the right, it doesn't matter what lesson we're looking at, but right now I'm on Chapter 4, Lesson 1. You'll see some thumbnails of animations that are in the lessons. We're not going to click on them now because we're going to use some of them in the presentation. So I guess I just wanted you guys to see how it's set up. Bryn, do you bring us back now, or do we just click the X to come back to the Blackboard?
So folks, you can either simply click the X to close the window, or you can click, if you want to leave it open, you can just move back to your Blackboard window by looking at the bottom of your screen and clicking on Blackboard Collaborate, or look for the icon. It looks like a purple circle with 2 white arrows inside of it, and that'll bring you back to the presentation. And you should be seeing Jim's slide with his face in the top left-hand corner.
Okay, I hope everybody was able to navigate a little bit and see what a standard lesson is like. Let's keep rolling. So basically, the lessons, like I said, are 5E format. They've got almost every chapter in every lesson has lots of hands-on activities. Actually, tonight, Chapter 4 is the exception. We do activities, but they're not so many of the classic kinds of things we do, like where you're going to be mixing liquids or dissolving stuff or doing a chemical reaction. The periodic table, in a way, some aspects that we think kids should learn about it, kind of hard to do through a classic hands-on activity. But we do have activities where kids can get up in the room and play a card game and things like that, and we'll show you what those are like. So anyway, we have mostly hands-on activities. We always have student activity sheets. That's an assessment or an evaluation part of the 5E in every lesson. On the activity sheet, mostly it's for kids to draw pictures or write descriptions or answer questions. And in almost every single lesson, I guess I would have to say everyone, there's some type of multimedia, either molecular animations or video. And there's teacher background in case you need your little recollection refreshed on some science content. And there's always student reading at the chapter level and a test bank, which you saw. So what do we plan to get out of this thing tonight? Well, I guess the main thing is we just want to show you the types of activities and resources we have in Chapter 4 of middleschoolchemistry.com. And this kind of stuff that you can use in the classroom very quickly and easily, so that's nice. And how do you think about whether it's the kind of thing that you can use? And we'll also review some basic chemistry concepts while we go through it. The vast majority of this you probably are very familiar with, but every once in a while, even when we go over basic content, teachers realize, oh, okay, now I understand that a little better. So we'll see. Maybe there's some stuff we can pick up here. Now, in every webinar we've done so far, we've always had a fascination number line. So anybody who's been with us before, sorry, we're doing another one. So this particular fascination number line is for you to indicate your level of fascination with the following question. What does the periodic table tell us about atoms? And why do atoms bond together to make molecules? That's a kind of question that one could ponder. And so we're asking you where your fascination range kind of is on this question. You could have 0, you've never thought about it and you're quite happy that way. 5, you're willing to listen if it doesn't take too long. Or 10, if you're like me, you would stay up nights just pondering this. And some people would think that's not useful, but hey. All right, we've got above 5 for most people.
Yes,
that's good.
And they're jumping in there. For folks who were not with us during our introduction and you're wondering where you'll be able to find those fun pieces of clip art that everyone else is using, it's on your long vertical toolbar, which is alongside of your participant window. Select the bottom button there and just pick a piece of clip art under common symbols, and then you can place that there on the number line.
All right, well, it's good to see that there are people, there are at least a couple people all the way out of 10. That's great. And anyway, if this is kind of just for fun, but let's try to get into these questions and see if we can understand them. And like I said, a lot of what we're going to do tonight you'll already be very familiar with, but maybe it's a little different take on it. And you can discuss in the chat with other teachers or with Adam or Bryn whether this is the type of thing that you would do, or you do something very similar, or you wouldn't do it this way and here's why. It would be nice if we had some people contributing there to the chat so I'm not the only one, you know, doing the talking. So here we go. Chapter 4, Lesson 1. The idea is for this very first lesson about the periodic table is not to necessarily look immediately at the periodic table. We're going to take a look at what an atom is made out of. In chapters 1, 2, and 3 in middleschoolchemistry.com, we almost always showed, or actually we always showed an atom or a molecule as like a little sphere or a little ball. And sometimes we gave it, you know, like the water molecule, we gave it a shape, and some other things we showed, but we never showed like the down at the level of what an atom is made out of. So this is the first time we're doing that. So we figured before we start talking about the periodic table and the fact like what a proton and electron are in terms of the periodic table, we should talk about them first right off the bat in Lesson 1. So here we go. We've got a classic kind of picture, which you've probably seen before, of a pencil point. It's made up of graphite. Graphite is made of carbon. So maybe we swoop out or swoop in and see a magnified view of the carbon. They're just made of carbon atoms. And then we pick one of those and we say, okay, this is a carbon atom. And for kids, I'm not sure the way you guys would approach this, but maybe a 7th, maybe 6th, 7th, or 8th grader would already be familiar with what's a proton, a neutron, and electron. So this might be a way to get at like sort of their pre-existing knowledge on this topic. You might say, like, if this is a carbon atom and this is the nucleus, does anybody know what's in there? The idea is you want to give kids an opportunity to say proton, neutron, and then you'd ask them, well, what do you think these little dots are on the outside here? Maybe they know, maybe they don't, but you want to eventually get to electron. So this first lesson, Chapter 4, Lesson 1, is really the real basics. So we tell kids, or they tell us, that the nucleus of the atom is on the inside, and it's made up of the protons and neutrons, and these things on the outside are electrons. And then we try to get a little bit of detail, and as you all know, we try to get them to say the protons are positive, the neutrons have no charge, and the electrons are negative. And that the electrons are as negative as the proton is positive. They're equal in strength but opposite in direction. Now, we also want them to know that a neutron is neutral. It has no charge, and that a neutron has about the same mass as a proton. So all this we do kind of in, I guess, using this picture and talking back and forth with the kids to see what they know and trying to get this kind of basic stuff out of the way. So let's go up here. So then we are at the point where we want to sort of investigate this idea of what's a proton, what's an electron, how they act together. So we have a molecular animation to show this. Bryn, could you take us there, and I'll talk people through how to use it?
Sure, Jim. Here we go.
So on this animation, if you guys go down to the button that says click to start and click that, you should see two protons. And here we would just ask kids, okay, we said the protons have a positive charge. What happens if we bring two protons together? Do you think they'll just, I don't know, attract each other? Do you think they'll repel, like push away from each other? You think they'll zoom around each other? Anybody have any ideas? Again, trying to get to the idea of what kids already know. So click play, you guys. Let's see what happens. So I hope that you were able to play this and that these two protons repel each other. Now, if you go down to these three tabs at the bottom, or three buttons, you can now pick two electrons. If you click on two electrons, let's see what they do. So you could ask kids, well, if two protons repel each other, maybe two electrons attract each other. Who knows? You want to finally get to this idea that if they have the same charge, they repel. So you can hit play on this one, and it should show the two electrons repelling. And then if you go to the one on the far right, one proton and one electron, you can ask kids what might happen here, and maybe they'll realize, I don't know, if the other one's repelled, maybe these will attract. So you hit play on this, and indeed they come together and attract. So we're just getting the very basics on this first animation. It also has a button on the lower right-hand corner that you could click if you wanted to replay the whole thing. But we're not going to do that right now. So I'm going to keep going. Let me get out of here. If you guys would X out of your animation, we'll go to the next slide. Here, we have we're still in Chapter 4, Lesson 1, and we're going to look at an atom finally. You know, we just looked at protons and electrons, but that's what atoms are made out of. So, Bryn, could you take us to this animation? Here's the hydrogen atom. Again, you guys, if you hit click to start, you'll see that here we have this very Bohr model idea of an electron going around a proton. Now, lots of chemists and scientists and teachers may say that this is a bad model, yikes, because it's an old style of thinking about the atom. But we think that it's useful, at least at a middle school level, to get some ideas across. What we do is we use this double-headed arrow to mean that the electron and the proton are sort of mutually attracted. One is like the proton is attracting the electron, and the electron is attracting the proton, and it doesn't crash in. The electron doesn't crash into the proton because it sort of has enough energy going around to keep it, to keep it at some sort of balanced distance. So it's attracted, but it doesn't crash and it doesn't fly off. Now, so this is why an atom stays together, because a proton and electron are attracted to each other. Now, there's a more sort of a more modern way of looking at this, and it's called the cloud model. So in the lower left-hand corner, you guys, we have this thing that says See Cloud. If you click that, this is sort of more acceptable by, I don't know, by scientists and, you know, people who want to talk about that the electron doesn't orbit the nucleus like a planet, you know, in a single plane. It's really in a three-dimensional region around the protons, or around the nucleus, and that at any given time it's sort of anywhere in that region surrounding the nucleus, and that's fine. And you can tell kids that you really can't tell where the electron is at any time, but it's like sort of makes like it's in the region around the nucleus and creates this atom, this hydrogen atom. Is really like a ball with a proton in the middle and an electron cloud around the outside. Same thing where you could repeat it if you wanted to in the lower right-hand corner. Okay, let's leave that one, you guys, and come back to the program here. So we didn't have a lot of opportunities for kids to do hands-on activities in Chapter 4, but we thought we would do something quick and easy with them about protons and electrons, just to give this idea of opposites attract a meaning. So, Bryn, could you run this video?
Sure, Jim.
It's just a very simple static electricity thing where we take a strip of plastic shopping bag, and you have kids basically run their fingers down the bag. You'll see. And then what we did was we took electrons from our fingers and put them on the bag, and so our fingers were a little bit positive and the bag was a little bit negative, and now we've got two charged pieces of bag, two strips, so they repel each other. It's just to try to have a sort of like a physical way of seeing this idea of attraction and repulsion. So you can click out of that. So I guess to round out this Chapter 4, Lesson 1, this idea of protons are positive, electrons are negative, that like charges repel, opposite charges attract. We have kids on the activity sheet make some drawings. Here, this is actually the explain portion of the lesson. And what we did, we tried to show that the plastic starts out as basically neutral. Your skin is basically neutral. You've got as many protons and electrons in the plastic, and you've got about equal number of protons and electrons in your skin. So they're both neutral. But then when you put the plastic through your fingers, you're actually stripping away, believe it or not, some electrons from your skin and sticking them on the plastic. So now the plastic has more electrons than it has protons, so it's negative. And your skin, since it lost electrons, it still has the same number of protons, but now it has more protons than electrons, so it's positive. So positive and negative attract. Again, it's sort of like a macroscopic way of seeing the unseeable. So, and that's basically what Chapter 4, Lesson 1 is. So let's go on with questions. Anybody, or Bryn, you can take over from here.
Sure, thanks, Jim. So folks, at this point, if you've got any questions on what Jim's covered so far, go ahead and type those into the chat. And I see, Leslie, you raised your hand. Go ahead and type into the chat and let us know what your question is. And Jim, we've got a question there from Tracy. She wants to know, why doesn't it happen the other way around?
That is a good question. There's no great reason. I'm trying to remember what this is called. I meant to look this up before I started the program here. There's a list, a sort of a comprehensive list of items that can be rubbed together which cause electrons to move from one to the other and not the other way around. For instance, like they know that if you rub, I think it's wool on amber, like the electrons go from the wool to the amber. But if you rub, you know, I don't know, cotton on wood, they might move from the wood to the cotton. There are ways of testing these combinations of objects, and I'm not sure if people really know the reason why one object loses its electrons to another. There may be a great reason, like loosely held electrons in some objects, in some substances for some reason, but we happen to know, because they actually had this on this list of stuff, that if you rub a piece of plastic, that the electrons are going to move from you to the plastic and not the other way. But your question's a great one. Why that is, I'm not sure. Are there other questions, Bryn, that we need to cover?
There's a lot of great comments coming into the chat there, Jim.
Oh, good.
But I think that let's see, I think these are just comments. Folks, if I'm missing a question, go ahead and bring it back up to us. But Jim, why don't we go ahead and keep moving for now? Okay.
So now, Chapter 4, Lesson 2 is finally we look at the periodic table. And, you know, it's a big, crazy-looking thing, as you know. There are ways to figure out how to interpret it. Let me grab a pointer here. What we do is when we show it, we don't spend a lot of time. You know, I'm telling you what we do, but you guys, of course, will do anything that works for you the way you teach in your classroom. So we're just showing you one possible approach. And I guess I should say here that we never, ever expected middleschoolchemistry.com to be like a curriculum that you would follow like a script. You know, we really want people to find something in here that they think is useful and plug it into what they already do. Or if they do find something that looks pretty good, you know, in its entirety, they should try it. You know, and obviously you guys are teachers, you know that you're going to mold whatever you find to your, you know, so that it works best for you. So whatever I do tonight, you know, don't think of it as prescriptive at all. It's just showing you one possible way. So anyway, the way we wrote this was that when you show the periodic table, we just take a piece of it. So we're just going to take one little section here, one element, carbon, and we're going to look and see what is this about? What does the periodic table tell us? How much information can you get out of just one little rectangle like this? Well, as you guys know, atomic number is a really important thing, so we spend a lot of time on atomic number, that it's the number of protons in the nucleus, and we make a big point that that doesn't change, that if you know that an element has 6 protons in the nucleus, it's got to be carbon. That's its identity. Then we also spend a fair amount of time with this annoying number down here that a lot of kids are somewhat intimidated by, a number like 12.01. Like, what does that mean? So I won't get into it too much here, but because we're going to play a little game where we get to work with this a little bit. But basically, this idea is the average atomic mass. Yike, what does that mean? Well, we look at the mass of carbon as the sum of the mass of its protons and neutrons and electrons, actually. Some people don't realize that the atomic mass does take into account electrons, although their mass is so small compared to the protons and neutrons, it's practically irrelevant, but it is there. But when we tell kids that we're going to try to figure out, like for instance, how many neutrons most carbon atoms have, we know that every single one has 6 protons, but how many neutrons? Well, protons and neutrons weigh about the same, and they contribute the vast amount of mass to the atom. So we'd say most carbon atoms have, well, they all have 6 protons, and the vast majority have 6 neutrons. Because 6 and 6 is 12, and this number is very close to 12. But it's 12.01. So that's kind of weird. So let's go on, and we'll deal with that in the next slide, that sort of strange 0.01 thing. So, I should mention also, we only really deal with the first 20 elements in the periodic table. So we kind of scrunch the periodic table down so that it's a little easier to handle, and it just goes from hydrogen to calcium. Um, you can learn a lot with just these elements. And I don't know, it's a pretty common approach. So that's what we decided to do. The periodic table, just elements 1 through 20. So here's this question that we're talking about. Why does carbon have this 12.01? Well, if the vast majority of carbon atoms have 6 neutrons and 6 protons, the average mass would be 12.00. But there must be some carbon atoms out there that have more neutrons. There are some carbon atoms that must have 7 neutrons to bring this number up a little bit. Now, this idea is not easy. For students, the idea of average atomic mass, that if it's 6 and 6 makes 12, so there must be some with 7 to force this number up a little bit. You know, that's something you'd have to work with kids for a while. But we tried in a card game that we have. I'll show you. We included in middleschoolchemistry.com 20 sheets of paper that are intended to be cut up and used to play 2 separate card games. So here's just these are just some samples. This is hydrogen's card, or hydrogen sheet of paper, and we have one for carbon and neon and calcium. We have one for each of the first 20 elements of the periodic table. And on the left are cards that you would use for a card game about protons, neutrons, and electrons. And you would basically, you'd cut out all these cards, and there's 20 sheets, and there's 1, 2, 3, 4, 5 cards each, so there's 100 possible cards. Maybe you have, 10 groups of students in your class. You're going to do this, groups of 3, so you could give each group 10 cards, and their job would be to go around and try to figure out the answer. I'll show you in a minute. Well, I'll show you right now. For instance, this one says, the atom you are looking for has 6 protons in its nucleus. So if a kid had that card, they would know right off the bat, oh, 6 protons, it must be carbon, because that's the atomic number. So, oh, I forgot to say, what we do is we take this upper right-hand card, it's called the element card, and put those around the room. So they're in 20 different places around the room. So when the kid finds the answer, they take this card and they bring it to that spot where carbon is. And here's another one. The atom you're looking for has 6 electrons surrounding its nucleus. Well, that is a point that, it's a pretty important point, that in the periodic table, the elements are, they're neutral. If it's got 6 protons, it's got 6 electrons. So you can figure out what an element is by knowing the number of electrons it has, as far as the periodic table goes. Now here's another one. The atom you are looking for has 6 neutrons, usually, in its nucleus. Now, that's a tricky one. How would you figure that out? So we help kids do a couple of these before we let them try it in a group. So the atom you're looking for has 6 neutrons in its nucleus. Well, that means that you need to find an atom that you would add 6, number of neutrons, to its atomic number, its number of protons, that are going to give you a number very close to the average atomic mass. So you'd say, what would I have to add 6 to give, what element could I add 6 to its atomic number and get its average atomic mass? Well, in this one, carbon is a clear answer, because 6 and 6 is 12. And if you looked at nitrogen, for instance, you'd say, if I added 6 to 7, I get 13. Oh, it's 14. That's no good. How about boron? If I add 6 to 5, I get 11. Hey, that's not bad. 10.81, that's almost 11. So actually, if you add, the atom you're looking for has 6 neutrons usually in its nucleus, it could be carbon, and it could be boron. It just so happens that the number of neutrons is the same in some atoms, but the number of protons is always different. Let's do just a couple more. We'll go on to actually, why don't you guys try it? Hey, Bryn, if we, like for instance, ask this one, this first one, the atom you're looking for has 4 neutrons, usually, in its nucleus. Bryn, why don't you help people, like, you know, how would they answer that? By putting little markers on the periodic table?
Sure, Jim. So what we're going to do, everybody, is it's going to be the quickest to the draw. So we're going to activate the clip art tools, or you can use your pencil, but the first 5 people to get their stamps up will have a chance to respond to this one. So we're not going to leave the tools up for too long, otherwise our board will be covered. But if you've got an idea for number 4, go ahead and put it there. I mean, not number 4, but the first card.
Yeah, just this first one.
Okay,
right.
There's a first. Go ahead.
Sorry, Bryn. Let's just take what we have so far. The idea is to, if the atom you're looking for has 4 neutrons, usually, in its nucleus, that means what could I add 4 to? What number of protons could I add 4 to get me very close to this average atomic mass? So if I add 4, let's say to beryllium, so 4 and 4 is 8. Well, beryllium's 9, so that's not right on the button. If I tried boron, that would be adding 4 to 5, which is 9, but this is 10.81, so that's no good. But what would I have to add 4 to, or what could I add 4 to that'll get me close to the average atomic mass? Well, if I add 4 and 3, that's 7, and this is 6.94. So most lithium atoms have 4 neutrons, because if they had 3 neutrons, well, some have 3 because it's 6.94, but most have 4 because it's very close to 7. Now that may be too hard for kids, but it does take some practice to think this way. It definitely took me a while, and I missed some because I didn't realize that some have more than one right answer. So, but we eventually did realize that and found all the ones that do. Hey, could we clear this and do another one? We won't spend too much more time on this. But how about this one? Whoops. Okay. How about this? I'm getting something on my screen. Not sure why. Okay, it went away. This second one here, the atom you are looking for has 10 neutrons, usually in its nucleus. So the idea is to find what number of protons you can add 10 to that'll get you very close to the average atomic mass. I'll give you a hint. This one has 2 right answers.
Okay, Jim, there's our first few answers.
Way to go. Those are excellent answers. Because you ask yourself, if I add 10 neutrons to 10 protons, I should get a number pretty close to 20, and I do. 20 point, I think that's 1/6, kind of hard for me to read it there. So it's definitely neon is definitely one of them. And then if I add 10 to 9 here in fluorine, I hit it right on the button, 19. So there's 2 atoms that usually have 10 neutrons in their nucleus. Anyway, we're not going to go through any more of these, but if you guys think that's too hard for kids, I understand. But I think after some practice, they would eventually start getting that. And, you know, what's the point? Well, the point is just to drive home that the atoms are defined by the number of protons. They have this thing called average atomic mass, and you have to take into account the number of neutrons. But you have this weird number sometimes, like 20.16, because it doesn't have not all, for instance, neon atoms have the same number of neutrons. And then you can talk about this idea of isotopes. So let's move on. Okay, so they play that card game, and then there's another whole set of cards on the right that had energy level drawings on them. So lesson 4.3 is about this sort of maybe a little bit more complicated idea of energy levels. So we quickly go through this idea that there are places around the atom or regions around the atom where the electrons can be. And I don't know how many of you guys do this with kids, talk about energy levels, but when we do live presentations at like NSTA conferences, the vast majority of middle school teachers do introduce this idea that there's an energy level that's close to the nucleus, one that's further out, one that's further out than that, and that they can hold different numbers of electrons. So there's really, I don't know if there's any other great way of doing this other than to introduce the numbers themselves, that the first energy level can hold 2 electrons, and the second can hold 8, the third can hold 18, but it fills up 8 first, and then the next 2, even though it can hold 18, the next 2 go on the 4th level. It's like a little confusing, but the way we stop right there, that's one of the main reasons why we stop at 20, is because this idea of 2, 8, 8, and 2, and then that's enough. Even though the third level can hold 18, we stop at 8 because the next 2 that bring us to 20 go on the 4th level. I know it's a lot to get into, and we do give kids a lot of practice with that because it's tricky. But one thing that we start off by making sure the kids understand at least the basics, that this first energy level is closest to the nucleus and that it can hold 2 max, and that the next level is further from the nucleus and it can hold, its capacity is 8. Right now this one has 6 though. So we ask kids, what is this atom? What must it be? So maybe by now, and not the majority of kids, but some kids are going to know, well, I could just count up the electrons because electrons equal protons. So if they count them up, there's 2 here and 6 here, so it's a total of 8. 8 electrons means it has 8 protons. Well, the number of protons defines the atom as the atomic number, so what's atomic number 8? And they'll look at the periodic table and they'll know that this must be oxygen. So that's part of this next card game. I'll show you. Well, here we give kids a periodic table of energy levels, basically. And it's to give them a little better idea of patterns that develop. There are some interesting patterns here. And you guys probably know this, but when I first realized that the first row here in the periodic table, just hydrogen and helium, only has 1 energy level. So the first row has 1 energy level. And the second row has 2 energy levels. And the third row has 3 energy levels. And the fourth row has 4. So it's like this, it's called the principal quantum number, is the number of energy levels that an atom has. Now, we don't teach that term to kids necessarily, but you want them to see that there are other patterns. Like if you look down a row, if you look down a column or a group, that they're going to have the same number of electrons in their outermost energy level. There's 1 in hydrogen, there's 1 in lithium, 1 in sodium, and 1 in potassium. And eventually that kids can understand that, well, if the electron in the outer energy level has to do with the sort of reactivity, the way a chemical reacts, that maybe these react in a somewhat similar way because they all have the same number of electrons in the outer energy level, valence electrons. And we ask that question, what do you notice are similar about the atoms if you look down a group? And you can see it if you look at this, this kind of, chart. All right, let's keep going. So here, let's quickly play the game. You guys, or Bryn, you can help us. Let's look at this one first. You're going to mark the thing that you think is right. This one you should get right off the bat. The atom you are looking for has this energy level model. What must it be? Correct. It's got to be. There's no question, because it's got 5 electrons, means it has 5 protons. It's got to be boron. All right, let's do another one real quick. How about this one down here? The atom you're looking for has, whoops, the atom you were looking for has 2 electrons on the first level, 8 on the second, 8 on the third, and 1 on the fourth. What must it be? Well, the folks who are putting their markers on potassium are right. All you have to do is add up the number of electrons. 2 and 8 is 10, and 8 is 18, and 1 is 19. The same number of electrons as protons. The number of protons defines the atom. Atomic number 19. So very good. So anyway, what we've done is just tried to give you guys a way to play these card games. Some teachers, when we do these sessions, have different ideas about how to play them, which is all great. Use them any way you want. We laminate ours so they will last. All right, we've got a time for questions here. Bryn?
Thanks, Jim. And everyone, we're curious if, in addition to your questions, that you've got comments or ideas on activities that you've done similar to these card games, or if you have any thoughts about how you might use this in the classroom, feel free to go ahead and type those into the chat. And we're curious to have your feedback on this as well. Again, if you have any questions, you can type those into the chat, and I'll bring those up to Jim.
Yes, somebody mentioned here using marbles with, I'm sure they meant shells, I think. I think that person might mean this idea of an energy level is also called a shell. And that I've seen these things where you put 2 marbles on the first sort of shell and 8 on the second, or you put any number in and then you can identify the atom. I'm assuming that's what that is.
Jim, it looks like we don't have too many questions for you. It looks like the teachers are having some good conversation. So I'm thinking, in the interest of time, why don't we go ahead and move on to the next section?
Excellent. All right. Now, one thing we point out to students is that because of the way the atoms are in the periodic table, like that they have increasing atomic number if you go left to right, which means they have an increasing number of protons as you move across, that has some ramifications. You can see some patterns. So this is a little surprising to kids, and maybe surprising to adults too, that as you move across the periodic table, the atoms actually get smaller because we're adding protons, so we're adding positive charge, and that attracts their electrons more, and it pulls the electrons in and actually makes the overall size of the atom smaller. So as you move across the periodic table, again, these electrons are all going to be on the same outer energy levels. They're all going to be on the second level, and as you add more protons, they're going to be pulled in tighter and tighter. Then as you move to the next level, well, these are going to be on the third, so they start off bigger, but then as you move across, they get smaller as you add more and more protons. And as you move to the fourth, they're on the fourth level, so it starts off bigger because they're further away from the nucleus, but then as you add protons, they're going to get smaller. So it's kind of interesting trend in the periodic table. Now, we put this chart in the teacher background material. It's basically what we just saw, but in a graphical way. And you could show this to kids if you wanted to. It's a graph of the atomic radius, in other words, the size of the atom versus its atomic number. So it's the same thing, but in a graph. So hydrogen starts us off, and then helium is a little bit smaller because it's further to the right on the first level. Then we move to the second level here with lithium, so it got bigger, but then as we move across, they get smaller and smaller. And then boink, it goes up at sodium on the next level, and then gets smaller and smaller again. It's kind of interesting graphical way to show it. We also showed to you guys in the teacher background something called ionization energy. And that's kind of interesting. That's the energy required to pull an electron from off the outside energy level of an atom. And it also has this periodic kind of trend. It jumps around a little bit, but in general, the trend is similar, where if you're going to, hydrogen it takes some amount of energy to pull an electron off, but helium, it takes more energy because it's got more protons and it's a stronger attraction. Then you move down here to lithium, and you've got a low amount of energy because here you've got only 3 protons and you've got an electron out there on the second energy level. You can pull it off pretty easily, but then as you move across, it more or less gets harder and harder to pull it off because you're on the same energy level, but you've added more protons. So this periodicity, this idea is why they call the periodic table periodic. It has these kind of periodic trends, this up and down. So one thing that I mentioned that we point out to kids is that substances in a group kind of react similarly. So we borrowed some cool video. We have sodium, which is right here, in water, and potassium in water, and they act kind of similarly. There'll be you'll see a piece of sodium will run around on here and it'll smoke and be active. Potassium will really, really be active. It'll run around on top. But then if you just move over a little bit here to calcium, it'll act differently. Bryn, can you show us these videos?
Sure, Jim. Here comes the first one, sodium in water.
So here you can see, well, obviously you see it's really reactive. If you throw sodium in water, you get all this hot reaction going on. So you get the idea. Bryn, can we go to the next one, just in interest of time? So that was sodium, and here's potassium, which is in the same. This is extremely reactive. And now, if you could argue that they're somewhat similar, that sodium and potassium are reactive. They run around on the surface. They heat up. And now, if you move over just one place on the periodic table to calcium, it's significantly different. It just bubbles, and most of it is at the bottom. Anyway, so our point. Well, one reason why we do this is that they're fun to see. And the other reason is that we want to try to suggest that elements in the same column act kind of similarly and somewhat different than the ones they're next to. We have another version of this. Let's see. Bryn, could you bring, let me just say really quick. Here we just take sodium in acid, different types of acid, and then potassium in acid, also fun to look at, and then we compare it to calcium in acid. Okay, Bryn, let's run that. So here's sodium in hydrochloric acid, 2 different concentrations, and in nitric acid, 2 different concentrations. And you see that it was pretty reactive. You have this brown smoke. Lots of cool stuff happened. Let's look at potassium in acid. So that was sodium. Here's potassium. Also very reactive. Lots going on. And now we'll take a look at calcium. Well, you know, there's something going on there, but it's not like as crazy as sodium and potassium. So these are videos that are kind of useful because it's unlikely you would do these in the classroom. Very unlikely, actually. Let's keep going. Okay, Bryn, you want to take it from here?
Sure, Jim, thanks. We had another opportunity for a break, and if you had any questions, you can type those in. But we're also kind of curious to hear from you, and you've been having some great discussion already in the chat. But what do you think might be most challenging for your students as they learn about the periodic table? If you've got responses to that, you can go ahead and type those in, and some teachers have already been responding to similar concepts. And I see we've got some responses coming in there, Jim, already.
You know, in the interest of time, should we keep rolling, or is there a particular question or comment do you think we should, this is not real. Oh, I'm sorry, go ahead, Bryn.
I was just going to say we had one comment or one question that you could probably answer or not. Quick, maybe you can answer. Someone asked about the brown smoke. Corrine wanted to know, many kids will ask about it. Do you know what it is?
Nah, I don't off the top of my head.
Okay.
There was brown smoke in sodium in acid and potassium in acid. Actually, I think there was some in calcium in acid too, but not as much. Yike, I'm not sure. I'd have to, we'd have to look at, I guess, what was that, nitric acid? Adam might know, but I'm not sure. We have to look at the equation.
And we've got some other folks chiming in that it's nitrous oxide. Chuck says nitrous oxide. Marguerite says nitrogen dioxide. A couple of different responses there.
All right. We're being very qualitative here with students, but you're right. Some kids might ask that, so we would need to. I don't think that we included that, what that brown smoke is. We just wanted them to see that there was brown smoke, but that's a good point.
Thanks, everyone, for the great discussion. And Jim, should we go on to the next section?
Yeah. This next section is, well, what we did was really about kind of the very basics of the periodic table. We don't go over what's a metal and a metalloid and a nonmetal, although that's a pretty common thing, but we just didn't do that. And we're not saying that you shouldn't do it, but you use our material any way you want to augment what you're already doing. Now, we have lesson 4.4 is about bonding, covalent bonding, actually. So we've got these atoms that we've learned about in the periodic table. Hydrogen, for instance, 1 proton, 1 electron. So why does it bond the stuff? In fact, that's a pretty good question because there's like no free hydrogen anywhere in the world. It's all bonded. It's either bonded to another hydrogen to make H2, or it's bonded to a bunch of carbons to make hydrocarbons, or it's bonded to oxygen to make water. But let's just look at H2. Why do atoms bond? So we took the approach of discussing bonding in terms of attractions. Let's take a look here. Like if two hydrogen atoms get near each other, why would they bond? They should be pretty happy the way they are. But in fact, the electron from one hydrogen is attracted to the proton in another, because if it can get close enough, it's going to feel some of that attraction, some of this positive charge. And exactly in the same way that an electron from this hydrogen is going to feel attraction to the proton in the other hydrogen. So although they maintain their attractions to their own proton, we didn't include an arrow showing that. Let's assume that. But we put these double-headed arrows in to show that there's this mutual attraction from the proton of one to the electron of the other in both cases. And that's really what pulls them together. Now, there's lots of textbooks that talk about that atoms want to have full outer shells, that they want to be like noble gases and all that. You know, they don't really want to do that, but their attractions result in that happening. There's got to be a reason why they come together, and what we feel is a decent way of explaining it is that it's the attractions we've been talking about between positive and negative charge. So let's take a look at another example. Oh, sorry, we can look at a animation real quick. Can you show us that one, Graham? You guys, just like the other ones, if you hit click to start, you see two hydrogen atoms here, and let's play And basically this just shows you an animated version of the drawing. That those double-headed arrows are supposed to indicate that there's mutual attraction in both directions. And that's really what caused these things to come together. If you look at these two electrons in the middle here, that's a pretty common way of picturing on a piece of paper what a covalent bond looks like. It's the electrons are shown to be between the two nuclei. So I'm going to click out of that. Here, let's keep going. And then the classic water molecule, it's really the same reasoning. Is why would hydrogen atoms, which are fine on their own, be attracted to an oxygen atom? Same thing. If they get close enough, the electron from hydrogen is going to feel the attraction from the oxygen proton, and one of the oxygen electrons is going to feel an attraction from the hydrogen proton. And if there's room on the outer energy level and the attractions are strong enough in both directions, they're going to bond. And this way, you know, there's this classic way of saying they're sharing electrons. So electrons are going to be shared between the oxygen and the hydrogens. And normally, we count them up. Even though they're shared, we say that now oxygen's outer energy level is full because it has 1, 2, 3, 4, 5, 6, 7, 8. The outer energy level can hold 8 electrons, and there's 8 there. Even though they're being shared, you sort of count them for oxygen, and you count them for hydrogen. So hydrogen's outer energy level is full. But they didn't bond, like we'd say, that they didn't bond in order to fill their outer energy level. It's their outer energy levels got full because they were attracted and they bonded. So anyway, it's more a result than a cause, I guess is what we're saying. Let's look at that one real quick, Bryn, if you don't mind. So you guys, if you click here, you can see we've got a big old oxygen atom and a couple of hydrogens. If you hit play, we show this idea of mutual attraction in both directions is what caused these things to bond. And you end up with full energy levels. There you go. Now, just really quick, water is kind of a special case. This covalent bond we're talking about, remember when we did hydrogen, those were exactly the same, H2, a hydrogen covalently bonded with another hydrogen, so the attraction was equal between them and the sharing was exactly equal. In water, it's a little different. The oxygen actually attracts electrons, even in the covalent bond, a little stronger than hydrogen does. So the sharing of electrons, even though it's happening, isn't not equal. So you have more electrons near the oxygen part of the molecule than you do near the hydrogen. Now, that's why water has this famous polarity, where this extra gray here just means that there's extra negative charge down here, and since the electrons are down here more, it makes this area slightly positive. That's sometimes shown with colors. Traditionally, negative is red and positive is blue. Yeah, that has lots of consequences that we talk about actually in another chapter, chapter 5. We talk a lot about the polarity of water. Oh, this is kind of neat. This is, we had an opportunity to do electrolysis here because we wanted to show kids that, you know, water is H2O, and that if you take a little device, I don't know if you guys have done this, but if you sharpen a pencil on both ends, you take 2 of them and connect a battery to them, you can use that device. We have a picture of it and a full description in middleschoolchemistry.com to show that the gases, oxygen and hydrogen, come off during this electrolysis. Could we run this, Bryn? And one of the points we make to kids is that, okay, so we're putting this in and there's a battery up there, that you get more gas at one pencil point than the other because water is H2O, so you've got twice the amount of hydrogen as you do oxygen. It's kind of neat. It gives, I don't know, it's a nice activity, and it gives kids a chance to get that idea of that they're both gases, really. And then, okay, there's this idea of a double bond, and we just wanted to show kids that, yeah, that makes sense too. That O2 is double bonded. Why is that? Well, the same reason that two atoms form a single bond. It's based on attractions. So let's, here, I'll show you. Could we run this one real quick, Bryn? So if you guys hit the start button, here are your two oxygens. And if two oxygens get near each other, they're going to feel attractions. And here, these, the two electrons shown close to each other here is the classic way of showing a covalent bond. So these electrons are shared between them. If you count them up, you've got 8 on the outer level of one oxygen and 8 on the outer level of the other. So those are full. And they're, that's why we have oxygen as O2. You don't have any free oxygen just hanging around. And then we, a lot of teachers start with ionic bonds first. We started with covalent bonds first. This is lesson 4.5, and this is the last lesson that we'll do. We only have about 4 or 5 minutes left. But we show the classic look of, we use sodium chloride just like everybody does, and it's got these chlorine ions, which are negative, or chloride ions, and sodium, which are positive. And in a minute, we'll show how they got that way. But this is like a salt crystal, or a tiny, tiny little crystal of salt. And then just because we think these videos are pretty cool, we wanted to show you guys just sort of one of these 3D molecular animations. Bryn, could you show that really quick? So these are, this is bird's eye view, I guess, and a super duper close-up of a sodium chloride crystal, where you've got those big green chloride ions and those smaller sodiums, and they're held together because the chlorine is negative and the sodium is positive, and they attract. But why? How'd they get that way? Well, we look at that, and it's actually a kind of a similar process that we talked about before, but instead of being covalent, it's ionic, which means that instead of the electrons being shared, they're transferred. And you guys know this. And we try to approach it in a very similar way. Attractions are what matter. So if you've got a sodium atom and a chlorine atom, the attraction that chlorine has for sodium's electron is stronger than the attraction that sodium has for chlorine's electron. So if an electron is going to move, it's going to move in this direction, and that makes you guys, I know this, that the chlorine, which originally had 17 protons and 17 electrons, now has an extra electron, so it's negative. The sodium had 11 protons and 11 electrons, but it just lost one, so now it has more protons and electrons, so it's positive. And so they come together because they're a positive and negative charged particles. So let's just go here. Can you show this one real quick, Bryn? Oh, I see.
Sorry about that, Jim. Picked the wrong one. Here we go.
That's okay. And if we click and then click play, it'll show that with this thicker arrow that attraction is stronger. So that's where how the transfer happens. That's the direction. Then it creates a negative chlorine and a positive sodium, and they attract. Sorry, I'm rushing through these because we only have a couple more minutes, but I just wanted to show you guys if you think any of these kinds of videos or animations would be useful. I want to show you what we have. So, Bryn, this is a kind of an interesting video, and I think this one might have audio. I'm not sure if it'll work, though, for you all. Let's see. Okay, that's pretty cool. I don't know if you guys could hear that, but basically it was sodium metal placed in chlorine gas, and you saw the really cool reaction, very, very, very exothermic reaction. And basically it's a poisonous gas and a very reactive metal, and when they react, they make what Adam Boyd likes to say, it's delicious to eat on French fries. It just makes salt. It's pretty cool. And that's a nice video to show kids. And then, you know, we needed a way to have kids experience this a little bit more. So we show an electron micrograph of salt that even on the tiniest, tiniest level, they're cubes. And, you know, they've seen this positive and negative charge, and that's they alternate in a pattern and make a crystal. And then we have kids do it using styrofoam balls. You guys may have done that before. There's lots of models out there like that. But we thought it'd be useful for kids to get their hands on that a little bit more. Oh, last thing, you guys. It's not ions aren't only just positive and negative. Sometimes it can be two positives and two negatives. Like, let me show you. The famous CaCl2, calcium chloride, works this way, where the calcium loses 2 electrons, 1 to each chlorine. So since the calcium loses 2 electrons, it becomes, instead of like just Ca+, it becomes Ca2+ or +2, because it's got 2 more protons and electrons. And then each chlorine becomes a 1- because they each got 1 extra electron. So then the 2 pluses combine with each of the minuses, and that's the way it works with ions. There always has to be, it always has to turn out to be neutral, have the same number of negatives as positive. So if you got a 2+ positive ion, it's going to combine with either a 2 negative ion or 2 negatives. Okay, Bryn, let's just, I think this is the very last slide, for me anyway. Can you show this one and we'll play it, and that'll be it. You guys, you can click to start. You see the calcium and the chlorine, and it's supposed to show that the pull by chlorine on the electrons from calcium is stronger than the other direction, so they go to the chlorines, makes them negative, makes the calcium 2 positive, and you've got your ionic bond. Let me see if we have any more here. Okay, so just in a super quick conclusion, I tried to get through a lot of material, and we just skimmed the surface, really. But it's nice to see, I think, or we wanted to show you that we've got a lot of molecular animations, and that you guys might be able to incorporate in what you're already doing. And we hope that you pick anything from what we looked at tonight, or go into middleschoolchemistry.com and find something that'll work well for you, and use it the way you think is best. Bryn?
Thanks, Jim, and everyone. This is our final way to wrap up here. If you do have any questions, you can feel free to type those in, but we thought it'd be fun to end on a note hearing from you and find out what activities or what content do you think you might be using in the classroom. And you can use your text box tool, or I see some very artistic folks having a go with the highlighter as well. It's looking good. So everyone, take a moment there and type up on the screen how you might be using the content you learned about tonight, and we'll move some of the boxes around so everybody's comments can be seen here. Lots of good stuff coming up, Jim. It looks like the teachers are excited to get back in the class and share this with the students. And with that, everyone, I'll go ahead and move on to our closing and give a big thank you to Jim for sharing so much great content and resources tonight. Everyone, let's use our emoticon button. That's the one with the face on it, to give Jim a round of applause. Thanks, everyone, and we'll give an extra round of applause to Adam Boyd there in the chat window, fast fingers, typing responses and URLs to everyone's questions. Thanks a lot, Adam, for helping out as well. And I would like to thank the sponsor of tonight's web seminar, the American Chemical Society. And a thank you to the administration of NSTA for their support for web seminars. We'd also like to give a look at our upcoming web seminar calendar. If you're an NSTA member, you can join us for a special event on the 22nd. Join us to talk more about the next generation science standards. Then on the 23rd, you can join us for a program in our NASA Explorer School series. We'll be looking at chemical elements, Genesis, what are we made of? And then on the 24th, join us for another NASA program, Temperature and Earth Climate, Modeling Hot and Cold Planets. You can register for these programs and more by going to learningcenter.nsta.org/webseminars. I'd like to thank everyone for your participation tonight and look forward to seeing you again on another web seminar.